Let's look at an example of a change of coordinate matrix applied to a linear operator. So here's a change of coordinate matrix, the vector space being polynomials of degree at most 2. Here's basis, the standard basis is beta prime, but I'm kind of interested in this standard basis, this other basis, 1, x minus 1, x minus 2, okay? So let's just consider a linear operator from degree, polynomials of degree at most 2 to polynomials of degree at most 2, given by the derivative of this quadratic ax squared bx plus c is, let's see, the derivative should be 2ax plus b, right? And then let's pretend like I wanted to start with the derivative in terms of beta prime, because that seems like the more intuitive one to start with. And you can get back and forth with this. So let's see. So I need d of all the elements of beta prime. So derivative of 1, derivative of x squared, shouldn't be that rough. I need to express them in terms of the basis. So what's the derivative of 1? Well, it's 0. So it's 0 of all 3 basis elements, right? Okay, and then what's the derivative of x? Well, it's 1, 1, no x's, no x squareds. What's the derivative of x squared? Well, it's 2 x's, no constants, and no x squared terms, right? And so the matrix representation of this linear operator is, this is my first column, row becomes the column 0, 0, 0. The second row becomes second column, 1, 0, 0. Third row becomes third column, 0, 2, 0. Okay, so now what I want to do is I want to be able to represent d beta. Okay, now what I want to have here is q beta prime, q inverse. If you multiply it on the right by q and on the left by q inverse, you might have the form that's going from beta to beta prime, but I'm switching it, and you can go either direction. So this is what I have. Now I have q up there, q inverse. You could calculate this yourself using any number of algorithms, but I just calculated it ahead of time. It is 1, negative 1, negative 1, 0, 1, 0, 0, 0, 1. So if I had that, let's see, q, that's 1, 1, 1, 0, 1, 0, 0, 0, 1. The matrix representation of d in terms of beta prime, 0, 1, 0, 0, 0, 2, 0, 0, 0. And then q inverse, 1, negative 1, negative 1, 0, 1, 0, 0, 0, 1. Okay, and matrix multiplication is associative, so let's see. So why don't we go ahead and multiply all that out. The first 2 row column is 0. Second row first column is 0. Third row first column is 0. First row second column should give me a 1. Second row second column should give me a 0. Third row second column should give me a 0. Let's see. First row third column should give me a 2. Second row third column gives me a 2. Third row third column gives me a 0. Okay, so I've got that. The last matrix is unchanged. Now I've got to multiply these. First row first column is a 0. Second row first column is a 0. Third row first column is a 0. You can slow down and check these manually yourself. First row second column is a 1. Second row second column is a 0. Third row second column is a 0. First row third column is a 2. Second row third column is a 2. Third row third column is a 0. Okay, so this is that matrix, right? Okay, so what does that give me, actually? That gives me, this gives me the matrix representation of D in terms of beta. And then, so if you want to apply it to any vector, I mean, I have a particular vector example up there, but it gives me the representation of that in terms of beta, okay? So if you want this, just takes the matrix we've pre-computed there, the representation of V in terms of beta, we pre-computed that right up here too, right? So let's see, what do I have here? I have 0, 1, 2, 0, 0, 2, 0, 0, 0, and this matrix representation 4, negative 1, 2. Right, let's multiply those. First row times column gives me negative 1 plus 4 is 3. Second row times the column is 4. Third row times the column is 0. Okay, so that is the representation of this element in terms of beta. So if you want to sort of double check, did I actually do the algebra correctly? You could sort of say, okay, well, what is that? dV I could manually compute. Remember, V was this vector. So I've got the derivative of the vector 2x squared minus x plus 3, and the derivative of that, you well know, is 4x minus 1, right? But how do I write that in terms of the beta basis? So in terms of 1 and x minus 1 and x squared minus 1. And this is a toy example. Can you see that? In fact, the way you'd write this in terms of this basis element, you wouldn't need any x squareds. You'd need 4 x minus 1s, but that would give you negative 4x's. And so you'd have to have 3 1s. And in fact, those are the coefficients. So you can do it in the toy example, but then you could do it in stunningly hard examples as well. Hope that helps.